Hello, and welcome to this course on using Python's append method. Lists are frequently used in Python programs that work with collections of data, and append is one of the most commonly used methods to work with lists. So in this fairly short course, you'll learn some of the best ways to use append. To see why this is useful, let's start by looking at the Python list. As I mentioned, it's common for a program to work on collections of data. The list is one of the most common data structures used to store and access those collections in Python programs. And the append method is the primary way data elements are added to a list. So if you're wanting to learn how to properly and effectively use the append method, then this is the course for you. Once you've completed this course, you should be able to write Pythonic code using the append method. Use the append method to populate lists in a for loop. Learn a popular alternate way to populate a list called list comprehension. And learn how append can be used in other types of data structures, such as arrays and double-ended queues, also known as stacks. This course is related to a tutorial based on Leodanos Ramos called Python's Append, Add Items to Your Lists in Place. And I do follow it pretty closely. So feel free to follow along with that tutorial as you go through this course. These are the software tools I use in this course. If you use other programs, then things will look a little bit different than what you're familiar with. For my program files, I use Visual Studio Code. I do have all of the code examples in the slides, but I'll probably describe the examples in VS Code. All of my code files are available by a link in this course, so you'll have both the slides and the actual files to refer to when wanting to look back at the examples. I'm working on a Mac, and I use iTerm for my terminal shell. For other systems, you might be looking to use another terminal, or maybe something called a command shell or PowerShell. For interactive Python, I use a REPL called PTPython. I like the way its syntax coloring looks in these lessons. So let's get started by looking at the basics of the append method. In this lesson, you'll see the basics of using the append method. The append method takes an object as an argument and adds it to the end of an existing list. For example, suppose you create a list and you want to add another number to it. You would do so by using the append method by first typing the name of the list, followed by a dot, then the call to append, putting in parentheses the object you wanted to add. And now you can see that 4 has been added to the end of the list. In Python, the elements of a list can be any type of object. And append can be used to add any type of object to the end of the list. So you can start with a list of integers. Add another integer. Then maybe a string. And then a decimal number. So any type of object you have to add to the end of the list, you can use append to do that. One way to interpret what append does can be through the use of slicing. You can start with a list, and then use a slice operation to extend it. So this notation will have the same effect as append. So what's happening here? You're taking a slice from numbers, in this case from 3 to the end, and then assigning that slice to an iterable, in this case a list containing a single element 4. Since there is nothing at index 3 yet, Python unpacks this iterable and places the individual items at the end of the list. However, you shouldn't take this interpretation too literally, because append only adds a single item to the end of a list. But using this slice operation will lead to different type of results. So again, I'm going to take a slice from positions 3 to the end and set that slice equal to a longer iterable. Since numbers doesn't have any elements there, Python will add them to the next positions in order in this list. So this list was extended by 3 elements to make room for 4, 5, and 6. That's using slicing. The append method doesn't function this way. If I try to append, helps if I type it right, numbers.append. If I try to append a list to the end of the existing list, we get a list of size 4, with the 4th element being that list, the first 3 elements still being those integers. So again, don't take this slice interpretation too literally. It only makes sense if you're adding an iterable with a single element to the end of the list. In the next lesson, you'll try to clear up some other misconceptions some programmers have when using append. In this lesson, you'll see 2 common misconceptions about the append method in the hopes that you won't try to use append the wrong way. First is that append only adds a single element to a list. Recall what you saw in the last lesson. If you create a list, and try to append another list to it, you don't get a new list with 6 elements, you get a new list with 4 elements, the last element being the list you just appended to the original list. See another example. Here you can create a variable for the original list and what you want to append to it. This time as a tuple, but it doesn't matter. Append still treated the tuple as a single item and added that as a 5th item to the list. This doesn't recreate the effect that the slice operation in the last lesson demonstrated. To do that, you'll need to use the extend method. This method adds elements from the argument provided as individual elements added onto the list. So here, if you again create a list, and this time use extend with the list you want to add on, you indeed do get a new list with the 6 elements you were expecting. And you can extend your list with a tuple, and it will again have the same desired effect, a new list with individual elements for what you were extending onto the original list. So use extend, not append, when you want to add multiple items to a list, which was the behavior you saw with the slice operation before. Another thing to remember is that append doesn't return a list to use. Append does its work in place. That means it actually modifies the object you call it on. It doesn't return a new or modified version of the list. Technically, it returns none, but that basically means you shouldn't plan on using it as if it's going to return something meaningful. So look at this. You can create a list, and while calling append to it, save the return value to a variable But when you try to inspect that variable, you don't see anything because it's a reference to none, which basically means it's not a reference to anything meaningful in this context. If you want to see the modified list, that's still in X. X itself was modified. The work was done in place. So again, don't try to use any return value from a call to append. Don't even save it. The list you use it on is being modified by adding the new element to the end of that same list. We call that doing the work in place. Next, we'll look at how append can be used inside loops to populate a list. In this lesson, you'll see one of the most common uses of the append method, which is populating a list from within a loop. A very common task in Python, and other programming languages for that matter, is to create a list iteratively. Here, you'll see how to do that using append inside a for loop. And in the next lesson, you'll see how that's done with something called list comprehension. But let's start with the for loop. To populate a list this way, you create a for loop which will iterate over the way you want to create each element. Then, in the same loop, call append to add that element to the existing list. Here is one example, creating a list of square roots of a collection of values. This function is going to operate by taking a list as an argument, saved to the parameter numbers, containing the numbers you want to take the square root of. Note that since we are going to be using a square root function, you should import Python's math module, which has that and many other useful mathematical functions. Before the loop begins, you create an empty list and save that to a variable. This is the list you are going to populate, one element at a time, each time the following for loop is executed. In this case, you're going to find the numbers to take the square root of in the collection provided in the parameter numbers. You need a variable to refer to each element in that collection. Here, it's called number. What do you want each list element to look like? Well, here it should be the square root of the number you're currently looking at. So you compute that number and append it to the existing list. You do this for every number provided in the argument. Then, outside the for loop, after it's completed, and it's very important to make sure this is outside the loop and not in it, you return the populated list. As an example, let's see how this will perform with a list of the first 9 perfect squares. Each one at a time, will have its square root taken, and then that value will be appended to the end of the list called result. So first 1 will be put in the list, then the square root of 4 is 2, will be appended to result, and then 3, and then so on. And the result is then displayed. To see this, let's run this script in a terminal window. It's called show square roots 1.py. So we run this, and here you can see the numbers in that list generated by the append method being used inside the for loop. This is a very common operation. So common that Python has a different syntax to perform the same action. It's called a list comprehension, and you'll see that next. In the last lesson, you saw how to populate a list using the append method inside a for loop. And that's a very important programming structure. In fact, we'll come back to that in the next lesson. But Python has developed a syntax called a list comprehension, which simplifies the code needed to perform that same action. It doesn't use append at all, but it's important enough that you really should see it in this course while you're looking at how to populate lists. Here's what that same function would look like using a list comprehension. The first thing you notice is the absence of a for loop. The list comprehension syntax does the iteration for you automatically. You begin with an expression in brackets, the brackets indicating that you're creating a list. The first thing inside the brackets is a model of what each expression in the list should look like. And here, since we're taking the square root of a number, you see the same expression that you saw in the append statement in the previous version. Taking the square root of a number, that was the expression for each element you were adding to the list. Same expression here. That's followed by the for clause, which looks similar to the for loop header. It identifies what you mean by the variable number in your expression. In this case, it is a single element inside the collection numbers. So this is a list of the square root of number for each number in the collection numbers. This script tests it with the same collection of perfect squares, displaying what this function returns. This is show square roots 2.py. You see the same output. This version saves that list to the variable result, which is then returned. But it's simpler to just return the list comprehension expression directly. You can modify this version. Not going to save it to a variable. Just going to return the list built by that expression. Save it. It's the same file name. And we can see the same results. List comprehensions are really great. They give you a short, concise way to build a list. But there are times when you really do need to use a for loop. And that's if you want to do additional processing inside the loop while you populate the list. And you'll see that in the next lesson. As you saw in the last lesson, list comprehension is a great tool for building lists with specific requirements. Much simpler syntax than using a for loop. But there are times you can't use list comprehension, and that's when you need to do additional work besides creating the list inside a loop. In that case, you need to go back to using the append method inside a for loop when building the list. Let's take a closer look. Remember, you're not only building a list, but doing additional tasks while the list is being populated. Here's an example. In this case, you want to keep track of how far along the loop is progressing as it computes the square roots. In this example, you want to create a list of square roots from a collection of numbers, but you also want to display where in the process each step is at. Notice here the for loop looks a little different, and not because we're doing additional processing, but in this case because of the specific processing this function wants to perform. After it adds each square root to the list, it wants to display as a percentage how much of the argument collection has been processed. To do this, it needs a variable to keep track of how much work has been done. So notice the difference in the for loop header. It's not for number in numbers, like you saw in the first version. It's for I number in enumerate numbers. What's happening here? The enumerate function does what you would expect it to. It numbers each of the item in the collection. In this case, it's also called numbers, starting with 0. It then returns a collection of tuples, each one unpacked into the variables I and number. There's an excellent real Python tutorial on enumerate if you'd like to learn more about it. So I is holding each element's position, and number is holding that specific item from the original collection. The function displays the number it's currently at, adds its square root to the result list, then computes how far it's progressed through the list, having saved the length of the list to the variable n before starting the loop. You would not be able to perform all of this additional processing using list comprehension. Coming over to the terminal window, you can see this work. This is version 3. Here you can see all of the output showing the progress of the function, and then the script prints the computed list, which is the same as before. So there you've seen another example of using append inside a for loop to populate a list. This time when the loop was supposed to do additional processing, and you aren't able to use list comprehension. In the next set of lessons, we'll look at how you can use append with other list methods to implement common data structures such as stacks and queues. In this lesson, you'll start to look at using lists with the append method and other list methods to implement common data structures. But let's start with some definitions. A data type is a type along with a collection of operations to manipulate the type. An abstract data type is a specification of a data type in a particular language, but not specifying exactly how the code should be written to implement its operations. And a data structure is an implementation of an abstract data type. There are many data structures, but in these next 2 lessons, you'll be looking at stacks and queues. Let's start with the stack. The goal here is to actually write the instructions to carry out the operations defined in the stack data type. We are going to implement the stack data structure. So, what is a stack? Like the name suggests, a stack is a data structure where you can visualize it as items stored on top of other items. It's often referred to as a last in, first out structure. The first thing you put in becomes the bottom of the stack, and it won't be taken out until everything else is removed from on top of it. The 2 main operations of a stack are push, to put a new item on the top of the stack, and pop, to remove the top item off of the stack. In this lesson, you'll use the append method to implement push, and list already comes with a pop method, which will perform that same action on the stack. So let's take a closer look at list's pop method. So create a list, and now you will use the pop method on it. The list method pop can take an argument, which indicates which item from the list is to be removed. The pop method also returns that item to the calling agent, assuming that it's intended to be used as it comes off out of the list. So if you call pop1 on this list, the item in position 1 will be popped and returned. We can see that the element 2 was returned. And if we look at the list, it now contains the numbers just 1 and 3. If you use pop without an argument, it pops off the end of the list. If you pop everything off, and then try again, you'll get an error message indicating that you tried to pop from an empty list. And there's what that message looks like, getting an index error. So here is an implementation of the stack data structure, making use of append and pop. Let's take a closer look. I've called this file list stack because it's the stack data type implemented using list. It's defined as a class, so it begins with the phrase class stack. Its initializer doesn't take any parameters other than the word self to refer to itself. It will just create an empty stack implemented with an empty list. The empty list is created and saved to the attribute underscore items. An underscore is used to indicate that this attribute should not be accessed directly, but the stack should only be accessed through the methods that are provided. And here are the implementations of the stack operations. Append is used to implement push. You want the top of the stack to be at the end of the list. So pushing an element to the stack means it needs to be added or appended to the end of the list. Pop is used to implement the operation pop. It doesn't use a parameter since you want it to pop off the end of the list. You see a try except block. This is because popping off an empty stack will cause an error, and you want the program to behave reasonably if that is attempted. The error you saw was an index error. So if this operation results in an index error, it will display empty stack. You see two other methods implemented here. When defining a class, it's common to implement several of what are referred to as dunder methods, whose name begin and end with double underscores. Here, it's implemented the dunder method len for length, so that the len function can be used on a stack object to see how many elements are in the stack. And the dunder method repr has been implemented to provide a way to represent this stack object in a print statement or in other contexts where its value can be displayed. It's often used for debugging purposes. Let's see this in action. First, import it. Now create a stack. Push some things on it. Let's see what it looks like. Get its representation. Print it. And find its length. Now pop some things off the stack. Again, see that the 2 was returned. And if we had saved this to a variable, we'd be able to use it. Similarly, 1 is returned. Now the stack is empty. And if you try to call pop on it again, you get the empty stack message that you saw in the pop method. So there's an implementation of a stack. Next, you'll look at implementing another data structure, the queue. In the last lesson, you learned how the append method can be used with other list methods to implement a stack. In this lesson, you'll learn how to use them to implement a queue. But first, what is a queue? A queue is a data structure that can be viewed as a pipe. You put things in at one end of the queue, and things come out at the other end. Or maybe like standing in line. You get into the line at the end and eventually work your way up to the front. It is a first in, first out structure. The first thing that gets in line or into the queue will be the first thing removed at the other end. There are two main operations. Enqueue adds something to the end of the queue, and dequeue removes the item at the front of the queue. It also returns that item to be used by the calling agent which asked for it. Implementing this with the list, again, append will be used to enqueue, add or append something to the end of the list. Dequeue will be implemented with pop, providing an argument of 0. This always pops off the element at the front of the list, which is being viewed as the front of this queue. So here's the implementation. This file is called listqueue.py because it's a queue data structure implemented using a list. And it begins class queue. The initializer is essentially the same. A list is created and saved to the attribute items. Here are the two main operations, enqueue and dequeue. Enqueue uses append to add something to the end of the queue, and dequeue uses pop with an argument of 0 to pop things off from the front of the queue, and that item is returned. Here again is that try except block used to react to an attempt to dequeue from an empty queue. Dunder methods len and repr have been implemented here, similar to how they were for the stack. And you can see this work as well. We create a queue. The initializer takes no arguments. Let's enqueue the numbers 1 and 2. And then inspect the queue. Again, just asking for its representation or asking it to be printed uses the REPR dunder method. And the len function will find its length since we defined that. And now remove some things from the queue. First was the 1. Notice how the first thing we put into the queue was the first thing taken out. This is one of the things that makes a queue different from a stack. First in, first out. So the 1 comes out first, and then the 2. There are other existing Python data structures that also have implemented an append method, and you'll see a couple of those in the next few lessons. So now you've seen a rather thorough introduction to how append is used with Python lists. Now you'll explore other types that use append. Many other structures in Python have an append method. They can be from a wide variety of modules, some standard to Python, some written by others. You'll finish up this course by seeing 2 of them, the array and the double-ended queue. First, the array. The array class from the array module, array.array, is another list-like structure, but it's much more limited. All of the elements must be of the same type, not mixed as you see in lists. And you can only use certain types, like integers, characters, decimal values, things that are considered simple types in the language C. Arrays do some things much more efficiently than lists. So if you're working only with numeric data, you might consider an array instead of a list. The initializer requires at least 1 argument. The type code indicates what type of data the list will contain. I for an integer, F for floating point, things like that. And you can optionally specify with a second argument an initial collection of values for the array. It's in the array module, so you can import it from there. Create a new integer array. With initial values 1, 2, and 3. And look at its representation. It displays itself with the type that it is and what the array currently looks like. You can inspect individual elements, including using slices, and modify individual elements in place. So the third element in the array at position 2 was changed from 3 to 4. As you saw, arrays support slicing, but they also support the append operation. So you can take our previous array and append to it. Calling .append. We'll add a 4th value. The last 2 values are now 4. And we can do this again. You can't use append to add more than 1 element. With individual numbers, or even to try a smaller list. I guess I'm up to 6 and 7. It doesn't like that either. But if you're curious, arrays do support extend. Elements in an array must all be of the same type. So if I try to append a decimal to an integer array, I get an error saying that it was expecting an integer and didn't get one. On the other hand, you can append an integer to a decimal array since integers can be cast to floats in C. So you can create a float array of decimal values and call append with an integer argument. And that integer will be cast to the decimal value 4.0 and then appended to the array. So the array is still an array of floats. It just took the integer, changed it by casting it to a float, and then appending it. So there's a look at using append with arrays in Python. Next, you'll look at using appends with double-ended queues. In this lesson, you'll see the append methods that work for double-ended queues. The double-ended queue structure is a class from the collections module. It allows for enqueuing and dequeuing off either end of the queue. It's pronounced dec. Calling it dequeue would create some confusion with the operation dequeue. So you say dec. You can perform the operations using pop and append to dequeue and enqueue off the right-hand side, and pop left and append left to dequeue and enqueue off the left-hand side. Its initializer takes two optional arguments, an initial queue and the maximum size of the queue, should you want one. Knowing how to create one and what its operations are, using it is like you would expect. First, import the class. Create a dec. With initial values. Notice we're back to using a more general type of Python collection, which can allow multiple types of data. You can append to it on either end. There it enqueued B on the right. And this enqueued negative 1.0 on the left. And since it's double-ended, you can pop off either end as well. First dequeuing off the right, and then off the left. Remember, the dequeue operation returns the item that was just popped off of the queue. And there's using dec's two append operations, append and append left. And that's the course. Next, you'll review everything you've done. Great work. Let's look at everything you've done. First, and most importantly, you learned how to use the append method. You saw how it's used to populate lists inside a for loop. And you saw a different way to populate lists using list comprehension. Remember, list comprehension is great, but if you need to do additional processing while building the list, you need to go back to the for loop and using append. You learned how to use append in other data structures like arrays and decs. Speaking of data structures, you also learned how to implement two very common data structures, stacks and queues, and saw how the append method is used in those implementations. Links to the code files and other useful information at RealPython are provided below. I hope you enjoyed this course, and I look forward to seeing you again in another RealPython course.